Okay, so now we're going to be starting section 3.4, which are some additional topics in probability, and we're going to be continuing and looking at some counting theory. So we're going to be looking at ways of grouping objects together in different ways, determining the ways of choosing several objects with regard to order, and without regard to order, and then we're going to use these counting principles to help us find some probabilities. So we're going to start off first with a permutation. A permutation is an ordered arrangement of objects. Ordered is an important word in this definition. The order in which we arrange these objects and choose the objects is going to matter. Now, before we look at the formula for permutation and continue on looking at permutations, we need to consider another definition. N factorial is denoted with n with an exclamation mark. It is equal to n times n minus 1 times n minus 2 times n minus 3, and so forth until you get down to 3 times 2 times 1. 0 factorial is 1, and so is 1 factorial. But for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720, and 4 factorial is 4 times 3 times 2 times 1. Now here's an example of how we might use permutations. Now in a Sudoku puzzle, we have the numbers 1 through 9 represented only one time in each row and into each column. So how many different ways can we arrange the first row in a Sudoku grid? Now it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, or many other orderings. So let's see how many different orderings we would have for the first row. Well, we would have 9 choices for the first, but once we picked a number, we couldn't use it again, so then we would have 8 choices, then 7 choices left, then 6, then 5, then 4, then 3, then 2, then 1, which is 9 factorial, which is really a permutation of n objects taken where we're ordering all n of them. So it's n factorial, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 362,880 different ways that only the first row could be ordered. Now, a permutation of n objects taken r at a time, where we have a set of n objects, but we're going to pick from the n objects r of them, and the order that we pick them is going to matter. Then that is equal to n factorial divided by n minus r factorial. Clearly, r has to be less than or equal to n, because you're choosing these r objects from this set of n. You cannot pick 10 objects from a set of 5, but you could pick 5 objects out of a set of 10. An example of a permutation would be a 4-digit code. Now notice, if my code is 4321 and your code is 1234, we have the same 4 numbers, but the order that we say them makes it a different code. So order matters when we're doing codes. So if I have 10 numbers, 0 through 9, but I cannot repeat any, so once I choose a number, I cannot choose it again. I'm out of these 10 numbers, I am choosing 4. All the different ways of choosing 4 numbers from the set of the 10 digits 0 to 9 is 10 factorial divided by 10 minus 4 factorial. Now notice 10 factorial is 10 times 9 times 8 times 7 times 6 factorial. This 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. So we're going to see later, we're not going to write this out. We're going to leave this as 6 factorial. We have a 6 factorial in the denominator, and they cancel. So all we're left with is 10 times 9 times 8 times 7. Now we can still use the fundamental counting principle that we learned earlier in chapter 3 by saying I have 4 digits that I'm going to choose for my code. I cannot repeat a number, so I have 10 choices for the first number. Then once I pick one, I only have 9 choices left. Then I have 8 choices for the third and 7 choices for the fourth. So I come up with the exact same answer, either using permutations or the fundamental counting principle. In either case, there are 5,040 different 4-digit codes in which no digit is repeated. Another example would be choosing the finishing of the Daytona 500, where finishing first, second, and third is different than if you finish second and someone else finished first. So the order that we select them for their finished position matters. Remember, with permutation, order matters. We had 43 cars in the race. We're going to choose 3 at a time. So 43 factorial divided by 43 minus 3, which is 40 factorial. 43 factorial divided by 40 factorial is 43 times 42 times 41 times 40 factorial, which we cancel with the 40 factorial in the denominator. And that means that there are 74,046 different ways that we can finish the Daytona 500 when you start with 43 race cars. Now, another way of looking at permutations is, what if I'm grouping together things where I can't tell the difference between them? Then what we want to know is how many are the distinguishable permutations of n objects, where we have n1 of one type, n2 of another, and so on. So n factorial divided by n1 factorial divided by n2 times n2 factorial times n3 factorial, and so forth, where when you add up the n1 plus n2 plus n3 plus so on to nk, they add up to n. This might be a little easier to understand if we look at an example. So for instance, suppose we have a building contractor and he's going to develop a subdivision. Now these subdivisions consist of 6 one-story houses which all look alike, 4 two-story houses which all look alike, and 2 split-level houses which all look alike. So in how many distinguishable ways can the houses be arranged? Well, we have 12 houses total, right? The 6 plus the 4 plus the 2. So we have 12 different houses total that go into the subdivision. But 6 of these one-story houses, I can't tell whether I pick one-story house 1 or one-story house 2 or one-story house 3. So there's 6 factorial different one-story houses. There's 4 factorial ways to choose the 2-story houses, and there's 2 factorial ways to choose these 2 split-level houses. When remember, what we're looking at here is you cannot tell the difference between these 6 one-story houses. They look exactly alike to you. So there are 13,860 distinguishable ways to design this subdivision so that you could tell the difference between the houses. The next concept to look at is the idea of combinations. In combinations, we're doing the same thing as we did with permutations. We have n objects, and we're going to select from these n objects r objects at a time. But this time, order does not matter. So it's known as a combination of n choose r, and it's n factorial over n minus r factorial. Remember, this piece here was exactly our permutation formula, and we're going to divide out another r factorial. An example of this would be the state's Department of Transportation plans to develop a new section of highway, and they're going to take 16 bids. Of these 16 bids, they plan to hire 4. Now, the companies do not care whether they were selected first, second, third, or fourth, just that they were selected. So the order that they were selected did not matter. So we're going to select 4 companies from this group of 16. Order is not important. So the formula is for 16 choose 4 is 16 factorial over 16 minus 4 factorial, and we're going to divide out an additional 4 factorial, which is 16 factorial, which is 16 times 15 times 14 times 13 times 12 factorial, which cancels with the 12 factorial in the denominator, and that's still divided out by the 4 factorial, which is 4 times 3 times 2 times 1, which is 1,820 different combinations of choosing 4 companies from this set of 16. One more example of a combination or a permutation is how we use them to find probabilities. Now, suppose we have an advisory board. This advisory board contains a chair, a secretary, and a webmaster. Now, whether you are the chair versus the secretary matters. So the order that I select you matters because I'm going to select the chair first, then the secretary, then the webmaster. So the order is going to matter. Thus, it's going to be a permutation, and only one of those favorable outcomes. Notice, we have a sitting board right now. So what's the probability of selecting at random the actual 3 members that hold each position? All right, so we had 17 students to choose from, and we're going to pick them 3 at a time where order matters, so it's a permutation. 17 factorial divided by 17 minus 3 is 17 times 16 times 15 times 14 factorial, divides out the 14 factorial in the denominator. So we have 4,080 different ways that we can select 3 students from this group of 17. Now, of those, only one of those sets of 3 is the actual 3 students who are actually on the board right now. So the probability of selecting the actual 3 members out of these 4,080 different ways of doing it would be 1 out of 4,080, which is approximately 0.0002. Another way of looking at the distinguishable permutations is writing out the letters M-I-S-S-I-S-S-I-P-P-I. Now notice, we have 4 S's, and if I put this S here and this S here, you can't tell the difference. It still looks like Mississippi to you. And the same thing, if I put this I here or this I here, it still looks like Mississippi to you. So we want to figure out first how many distinguishable. Now if I write this M and I switch the I and the S, you can tell the difference. It will not look like this word any longer. So we need to look at distinguishable permutations. So we had 11 letters in Mississippi. Of those, we had one M. We had 4 I's, 4 S's, and 2 P's. And so we divide out the 1 factorial for the M, the 4 factorial for the 4 I's, the 4 factorial for the 4 S's, and the 2 factorial for the 2 P's. Now this is, there are 34,650 distinguishable permutations of those given letters. Okay, that means I can tell the difference between, there's a little over 34,000 different ways to write Mississippi where it doesn't look like Mississippi anymore. Of those, exactly 1 actually looks like M-I-S-S-I-S-S-I-P-P-I. So 1 out of 34,650 is approximately 0.000029. That's the end of section 3.4. Now it's time to go to the Course Compass website and try the homework problems for 3.4. Thank you.